Hello, welcome back. So yeah, today we're gonna continue our uh, lecture on ConvNet. So as a brief review, we previously covered the convolution operation. We started from one dimension convolution and extended to two-dimension convolutions. So we introduced some terms like stride, padding, right? And we first look at a input image that is black or white, which has just one channel. And if the image is color, then it has multiple channels. It has three channels usually. So in order to apply convolution on the image that has three channels, it is important to have a filter, a convolution filter or kernel that has the same number of channels. Okay, so it's basically it's no longer no longer sliding window, but a sliding little volume within the inputs cube. Okay, and that will result in some outputs whose size can be computed by the formula that involves the number, the input size, the filter size, the whether there's a padding or not, and the size of padding and the stride. Okay, and also we mentioned that there could be more than just one filter, and if we have multiple filters, and the result of a convolution operation would be like also a cube that has multiple channels, or you can also think of a channel as a slice. Okay, it's a little slice of matrix. So if we stack multiple slices together, it becomes a cube. And in practice, we will find that in a typical convolutional neural network model, we can place multiple, actually a lot of filters in one layer, and that will result in, that will make the output from this layer quite thick, because it has so many channels, and each channel corresponds to one filter. All right, so we will take one more step from the convolution operation to the definition of convolutional layer and then pooling layer, and then we will combine these two types of layers together into some simple ConvNet models. Okay, so a convolutional layer is actually built up on the basis of the convolution operation, and we basically add parameters, and we define the parameters in a more formalized way. Okay, so this is the basis for the convolution layer, which is a convolution operation. Okay, so given the input that has three channels, okay, no matter what the width and the height and width is, the number of input channels is usually three. Okay, so the filter is also that has three channels. Okay, say we have two of such filters, and each one of them will result in a 4x4 output matrix, or output tensor, or output cube, whatever name you want to use. So now we're gonna add a ReLU activation upon that output. And before that ReLU, we also plus some bias terms. Okay, so the bias term will be added to the outputs, to the 4x4 outputs. And remember, the output is the result of this convolutional operation. Okay, so it is after the convolutional operation that we add the bias and apply the ReLU. Okay, so the bias and the ReLU, they are both element-wise operation. It's kind of, we add the same bias to each cell, to each elements in that output matrix, and we apply a element-wise ReLU activation, and of course you can use basically any type of activation functions, but the usual choice is ReLU activations. Okay, so we will get some new activation, right, from the ReLU activation function, and also for the second filter we will apply the same bias term and the ReLU. Okay, so one detail about whether the biases are the same parameters or not. So it's usually they are different. So each filter, say this is the filter 1, it should be this filter 1 should has its own bias term B1, and this second filter F2 should has its own bias term B2. Okay, so nowadays when we use frameworks, PyTorch, say we can define whether we can include whether we need the bias term or not. Okay, and I think the default is that the bias is included by default, and that bias term is associated with the filter. So different filters would have different bias parameters. All right. So, and then we combine the outputs from these two filters. We will have a 4x4x2. So this last dimension 2 is the number of filters we use. Okay. So that's basically how we add the activation functions. So now if we make some analogies to the regular neural network, which is the fully connected neural network, then because we have used the term Z, right, to indicate the results of the linear computation. So we can also kind of think of the outputs from the convolutional operation as some sort of Z's here, okay? And we can think of the filters used in this layer as the W's. It is the parameter weight matrices that are used to compute the Z's, okay? And the last part here, these are just the A's, the activation, the final output activations. Okay, so it can be basically we can use the same expression to kind of describe what this whole block on this slide is doing. It's basically doing carrying out some computation that is analogic to the regular neural network. Okay, so because previously we have defined the dimensions for the W's very clearly, okay, and the B's. So now we're gonna look at how many parameters we will use in this one layer of ConvNet. Okay, so before I leave this slide, when we talk about one layer, we are actually including the convolutional operation and the activation functions. So it's kind of 2 steps. Okay. All right. So we'll look at the number of parameters because it will be an interesting comparison with the ConvNet with the regular network. Okay, and ideally we want to see whether the ConvNet will save us a lot of memory space, because we have shown at the beginning of this lecture, we have shown that the regular neural network doesn't do well in modeling large pictures with limited parameters. Okay, so now if we look at one filter, then in this particular example, it is a 3x3x3 little cube, which has 27 parameters in each in total, right, in each filter. And say, what if we have 10 filters in this layer? Then the total number of parameters is simply 10 times that amount, which is, and of course we should apply this bias terms. Okay, so each filter comes with its own bias term. So that will be 28 times 10, which is 280 parameters. Okay, and good news is that that's it. That's the total number of parameters associated with that layer, okay? And no matter how big the input image is, the number of parameters remain fixed to 280, okay? So if we go back to the previous slides, for very tiny images that has 6 pixels by 6 by 6 pixels, it is 280 parameters. If it's 60 by 60, it's still that many parameters. If we don't change the filter size, if we don't add or include more filters, the same number of parameters will be used. Even for 300 by 600 by 600 or even larger images, it'll be basically the same number of parameters. Okay, so that is one big advantage of ConvNet. Does the bias term represent W0? I'm not sure what you mean. So W0, no, we don't have W0s. So the first layer, we usually call it W1, and the one within the upper, within the, and one is in the box, square brackets as a superscript. Okay, we don't have W0s. In any case, I don't think it appeared in a regular neural network either. Okay, so this is such a big advantage, right? So say, let's compare it with a regular neural network. Say, if we, in a regular network, we want a hidden layer to have 50 units, then it depends on the input size. What if the input is 64 by 64? Then it's already a lot of parameters. The weight matrix in the first layer is 50 times 64 times 64, right? Because in the regular way, in the regular neural network, we basically need to take all the pixels and place them into a long vector, which would result in a 64 times 64 long vector. And we need to times that with the number of hidden units. That is already 20K. And not to mention that the image could be further bigger, which will result in insane number of parameters, which is not practical at all. Okay, so that is a huge advantage of convolutional networks. And one more good news is that the convolutional neural network, it almost always have better performance than regular network in capturing the higher level properties or higher level features all within the image. Okay, it is a very performant and efficient way to capturing the features, in capturing the characteristics in an image data, in image data. Okay. So let's now look at some more notations. Okay, here are a bunch more formalized notations, but I think the excuse me, the mathematical notations themselves are not that important than the underlying computation, the principles of computation, because the notations can change, right? Or if I, in the different slides, I may use a different notation, I may use different ways of the writing the brackets, right? So the notation is not the most important thing, but we do really need to understand how the convolution operation happens and what and the mapping between two layers. That is the most important trick here. So we look at a convolutional layer, L, right? And then we can use the lowercase f with L as superscript to indicate the filter size for current layer. Okay, so the filter size is usually an odd number. It could be 3 or 5 or 7, but now people would tend to use smaller filters, and some people even use filter of 2 or even 1. That is a very interesting case. So a filter with 1 basically takes 1 pixel out, which doesn't do any convolution operation at all. But that one filter size of 1 is useful in some cases. Okay, and the P is for padding, right? Remember padding. Before we apply the convolutional layer, we can apply some thin frames, add some frame outside the inputs, right? And if padding is 1, it means we add 1 pixel at each direction. If padding is 0, it's called valid convolution, which means we don't pad at all. And then if we pad the input image by the size of the filter -1 divided by 2, and of course the filter should be a odd number in this case, then it will basically create the same output size. Okay, so that's padding. And also stride, we already mentioned that stride is the step, right? Step size that you move your filters. Okay, so that's for layer L. And then the inputs for layer L is defined in such a way. Okay, the first dimension is the height, second dimension is the width, and the last dimension is the number of channels. Okay, and they all have the L-1 as superscripts because they are from the previous layer. Okay, so here's one technical trick that's in the slide. We put the number of channels as the last dimension. Okay, but in the programming conventions of PyTorch and probably TensorFlow as well, the number of channels is usually used as the first dimension. Okay, so you will see in PyTorch that the input image has the dimension of NC times NH times NW. Okay, so that is a different order of the dimensions, but it's essentially the underlying data. It's the same cube-ish data or volume. Okay, and now that is the input from the previous layer, and the output layer from layer L, it's defined also by such 3 dimensions. Okay, and the NCL is different from the NCL-1. That is important. Okay, because we know that the NCL, the number of channels in the current layer, is determined by the number of filters used in the current layer. Okay, and the relationship between the currents, the height and the width of the current layer can be computed from those previous parameters, those previous heights and previous width, with the paddings, filter size, and strides considered. So that is basically the principles of computing NH and NW in the current layer. Okay, so we mentioned this in the basic operations. All right, and the technical trick here, the number of channels in the current layer is the number of filters, right? We also mentioned that, and it's important to note that it has nothing to do with the number of channels in each filter. Okay, and the shape of the filter here is determined by the number of channels in the previous layer. Okay, we also mentioned that here. I think you can think of it as a brief review. Okay, so the pink parts, they are the equal value. Okay, so number of channels in the previous layer determines the number of the channels in the filters here. Okay, all right, so the activations is of the same size of the outputs of the from the convolutional operation. And one more thing about the dimensionality, about the vectorization, is that we put multiple images in a batch, in a mini batch, right? So that will result in one more additional dimension here, which means that we have m such cubes in one batch. Okay, so when you do a image classification model, when you train a model, the data loaded is usually have for the data one mini batch usually have 4 dimensions. Okay, so because the different frameworks handle the dimensions in different orders. So in PyTorch, it could be m times nc times nh and nw. Okay, so it's basically depends on the frameworks you are using. Okay, so if we consider the number of parameters, right? So that's the computation we did before. We used 3 times 3 times plus 3 times 3 times 3 plus 1 times 10. That is a previous computation. But if we use a more general principle, it's basically the filter size times itself times the number of channels in the filter and times the number of filters. Okay, so of course this computation doesn't consider the bias terms. Okay, because bias terms, relatively speaking, it's small parts of the parameters. Okay, so the bias term is here. Okay, the bias term is a one parameter that has that many bias terms because it is the number of filters used. All right, so hopefully these slides would help you have an overall review of what kind of parameters and what's their relationship between the previous layer to the second layer. Okay, so I think probably the most important matching is the number of channels. Okay, and the number of channels would define how many outputs. So the number of filters will define the number of channels in the previous in the next layer, and the previous number of channels define the number of channels in the current filter. So in a framework that will be handled like you can specify when you define the filter or when you define the convolution operation, you can tell the function that I want that filter size, I want that number of channels. That is my, so here's my input channel, here's my output channel. So the framework will initialize every parameters for you, like semi-automatically. We will have that practice in programming assignments for this chapter. Okay. So let's look at first use a visualized way to look at a simple ConvNet and how that is defined. All right. So this here we have more serious data, right? It's although it's still a small data points, small image data points. It's 39 by 39 pixels, right? That's our input image. So we can use the superscript 0 to indicate the input. Okay, so the height and the width and the number of channels is like this. So for example, we use a filter, a 3 by 3 filter. Okay, the filter size is here, and we don't have any padding, and we use strike 1, and we use 10 of such filters. Okay, so this 3 matches the 3 here, right? And the results of applying these 10 filters will result in a cube, which is in that dimension, 37 by 37 by 10. Okay, so these 10, the last dimension, matches these 10 filters. Okay, and this, where is this 37 from? So it's basically 39 minus f m plus 1, right? That is 37. Okay, and if we observe the shape, if we look at the shape of the output, it's basically a shrinked cube from the two directions, from the along the width and the height directions, they are shrinked, but along the depth direction, the number of channels increased. So it's basically become thicker, but narrower, right? So we can further apply one more, and also we remember to apply the ReLU, right? And that will result in some activations. So next step, in the next layer, we can apply a slightly different filter. Say we have a 5x5 filter, but also with larger stride. Okay, so this larger stride means that the resulting width and height will be even smaller, because each time we move window, we take larger steps. Okay, so that will further shrink the images into a narrower height and narrower width. Okay, but we set 20 filters, so that means the outputs will be 7 by 7, 17 by 17 by 20. Okay, it's a very long cube now. Okay, all right, and we are not done yet. Let's still apply one more layer with even more filters, which will result in a 7 by 7 by 40. Okay, so this is a very long stick now. Okay, so let me mention something here. So the reasons why we set these filters is basically the results of a lot of empirical experiments. Okay, so actually this one, the current architecture, is based on a famous paper by the French mathematician Yann Latin, and his work is basically a revolutionary work that's first trained the so-called network called LaNet that has a similar structure shown in this slide. Okay, so we are basically following that research paper by setting the network structure in such a way. Okay, so now we have the third layers, activations. So now we notice that it's already very narrow. It's like 7 by 7. So it's a very small pixels in each channel, although it has a very deep, it's very deep cube. So it is probably a good time to no longer apply the shouldn't the dimension of A2 be, no, the stride is 2, so you need to divide it by the 2. So you need to use 37 minus 5 divided by 2, which is 16, and 16 rounded to floor, and plus 1, which is 17. Yeah. So yeah, the stride will significantly reduce the size, right? Because it's a division here. So now let's flatten all the outputs elements in this cube. Let's basically take all the elements out and put it into a long vector. Okay, and that will result in 7 times 7 times 40, which is 1960 units. Okay, so now it's time to use some regular neural network. Okay, because we can think of it as an input vector, and we can directly connect to one neuron as the outputs, and this neuron will do some classification, say whether this number is 3 or not, right? So the primary advantage of this forward pass is to reduce the size of the data. Yes, so it's basically we can, from a higher level speaking, we can say this is a feature extraction process that compress the data, right? Given the data that has many points in it, we use 3 steps or 3 layers of convolutional operation with activations. we try to extract some dense vectors representations of the image. Okay, so this last layer, the last output, this 1,960 units, this vector, it basically is a condensed representation, a highly compressed representation of the input image. Okay, so the interesting thing is that if we train a model on a large amount of data for sufficient amount of epochs, then this internal representation or this hidden layer representation, it basically shows some spatial distributions. If we visualize how this long vector look at its location in a high dimension space, then you will see that different numbers, they have different spatial distributions if we use this hidden layer as to represent that image. I think you are basically correct. It's a way to reduce the size and to come up with some useful dense vector representations. By useful, I mean this dense vector, this 1,960 units, it captures the key information. It captures the key features in the input image. Okay. So yeah, that's the overall structure. Okay. So the general trend is that if you look at the numbers here, the pictures become narrower, the height and the width become smaller, and the number of channels goes up. That is the typical trend of the convolutional layers happening here. Okay, so that's the convolutional layer so far. So next we're gonna look at another important layer called pooling layer. Okay, so this pooling layer, the most important characteristic is that it doesn't have parameters. It's not like the convolutional layer. One convolutional layer, it has the parameters in the little cube in the filter, right, and the bias parameter. But this layer, the pooling layer, it simply does, for example, in this, using this max pooling as an example, what it does is to pick up the maximum elements within the region that the filter is covering. Okay, so when the filter first covers the upper left region, for 2x2 region, it will choose the 10, pick up the 10, because 10 is the maximum element among these four. Okay, and then because we use stride 2, which means we take 2 pixels in one step, so it will take move 2 pixels to the right. So in the second region, in the yellow region, it will pick up among these elements. So in the case of a tie, it will probably pick up a random number. Okay, so it will pick up the 4, and so on for the rest of the regions covered. Okay, so the result is this basically downsampled. Okay, we basically select the most representative elements within this larger region. We select those maximum elements and we think of their most representative of the data. So we select these data, okay, as the output. So max pooling is useful in picking up the most salient elements, in picking up the most salient features in the data. Okay, and it can significantly reduce the size of the representation. Okay, so the idea, intuitive idea, is that we want to preserve the most salient features. If its features stand out by having larger magnitude, by having larger values, then we better preserve them in the outputs. Okay, so it basically has no parameters to learn. Okay, so let's look at a 3D volume max pooling case. So it's kind of similar to the 3D convolutional volume, and we have the filter, the polling filter, which is also 3 by 3, and we take the stride by 1. So the results now it's kind of different. Okay, so it's not a 4 by 4 by 1, but a 4 by 4 by 3, because we take the most the elements, the maximum elements within each channel. Okay, so it's not within the cube, but within the channel we take out the maximum elements. Okay, it applies to channels independently. Okay, so the output has the same number of channels as the inputs. Okay, this is kind of the different place from the convolutional layer. Okay, so another pooling layer is called average pooling. So as the name indicates, we basically compute the average outputs of all the elements within that region. Okay, so the 6.75 is the average value of these four numbers, and these four numbers will compute the average value. So this average pooling is a more gentle pooling by considering all the features in the original data. But actually, it turns out that max pooling is used much more often, because in most classification, in supervised learning cases, the most significant features are more important than the overall information, than all the average information. Okay. So let's look at pooling. If we define a pooling layer by specifying the feature size and the stride size, so these are the common parameter choices. Okay, so the pooling layer is usually have a larger stride with stride 2, and the inputs channel has that many channels. The output will have the same number of channels, and the new width and height is basically the same principle. We need to divide it by the stride. Okay, so that's the general principle of applying a pooling layer. Okay, and padding is rarely used, and no parameters learned. Okay, so yeah, so we have all the building blocks introduced. Convolutional layer, pooling layer. So now we're gonna again use the original LeNet 5 as a complete example showing how the neural nets, how the convolution layer and pooling layers can be put together. Okay, so the original experiments conducted by Yang Li-Tan is the MNIST data, which contains the handwritten digits. So we want the machine learning model to recognize which digit this image corresponds to. Okay, so it looks at 3 or looks at 5. So the machine we want the machine to learn which label this image has. Okay, so the input is quite small. It's a black or white image, so it has just one channel. So the original model of the LeNet 5 has the filter of size 5 and the stride 1, which results in a slightly smaller but thicker thicker outputs, and it has 6 in the output channel. So that means we applied 6 of such filters in this layer. So that's the first convolutional layer. We call it conv1, and then we apply a max pool layer with filter size 2 and stride 2, which will result in a 14 by 14 by 6. Okay, that's first pool layer. Notice that here the 6 matches 6 here, because pooling doesn't change the number of channels. Okay, that's conv1 and pool1 does. So in that paper, they call it this combination between conv1 and pool1 as the first layer altogether. Okay, so that is also a convention in convolutional neural network studies that people would usually consider a ConvNet appended by a polling layer as one layer. Okay, so that's the first layer, and then we applied more filters. That's the conv2. Okay, the image becomes much thicker, right, and smaller. And again, a max pool, which has even smaller, 5 times 5 times 16. That's pool, second pool. Okay, and now it's time to flatten. Okay, and we have 400 units in the hidden layer, and the second hidden layer, which has even smaller, 120, and the third hidden layer, smaller, and then becomes a softmax layer with 10 outputs. Okay, so the net 5, the 5 in the name indicates that we have 1, 2, 3, 4, or actually, no, it's not like this. It's actually 1, 2, 3, 4, 5. Okay, I guess it should be this way, like 5 layers before the output softmax layer. Okay, so the common patterns is that the convolutional layer is followed by a polling layer. Okay, and there will be some fully connected layers near the end. Okay, so this paper kind of lay out the paradigms of how convolutional neural network models should be designed. And we will see a lot of common places when we compare later models, say AlexNet, VGGNet, ResNet. It's basically a lot of similarities with the original Net5 network. Okay, and if we look at the number of parameters in the Net5, okay, the number of activation, the input has that many pixels. So the ConvNets, the first conv layer have that many parameters, and the pollings don't have parameters, right? So the second conv layer, that many. So you see that the majority of the parameters actually exist in the fully connected network, right? Because the fully connected network needs to consider all the inputs units, and the shape of the weight matrix is decided by is basically the product between the inputs size and the hidden size, right? So that's why the fully connection layers, they are very expensive. They are more computationally expensive compared to the convolutional network. Okay, so that is a first full example about ConvNet. Here's just another simple example of the ConvNets that has more layers, right? And you see that it's not like a fixed rules of whether we should put pools. The pools can also come after like 2 conv layers, okay? 2 conv layers, 2 ReLU activations. And it's almost the case that the last layer would be a fully connected layer connected to a softmax layer. Okay, that is a typical paradigm of using convolutional neural network to do classification tasks. All right. So next, we're gonna look at more concrete examples for different types of ConvNets from the literature. Okay, so before we start, let's look at the outlines. We'll briefly review the softmax layer a little bit, and because this layer is a special type of layer that has very different setting of parameters, and it's kind of related to the logistic regression outputs, which has just one unit, right? But now we have multiple units, because if we want to do a multi-class classification, then softmax layer is something we need to use. Okay, and then we'll cover several classic networks. This one, the net is already covered, so we'll quickly go through AlexNet, VGG, and ResNet. So the ResNet is the most special type among these two, and it's basically introduced the shortcuts, the concept of shortcuts, which significantly increase the flexibility of neural networks in capturing the features within image data. Okay, so I think we will have the time to go through the softmax layer today. Okay, so let's do that here. So the softmax layer, it's a layer for multi-class classification problems. Okay, so it's sometimes called softmax regression, but really it's not a regression problem. It's a classification problem that they deal with. So for example, in the famous CIFAR 10 datasets, it has images that have coming from 10 classes. Okay, it's from airplanes to animals to ships to trucks. So it's 10 classes. Okay, so we have the labels from 0 to 9. Okay, so a softmax layer will use a smaller subset to demonstrate here. Okay, so the size of the layer is the number of classes. Okay, it's decided by your problem. So if you want to classify 10 classes, then you need to set the layer to have 10 outputs. And if your problem is simpler, you have 4 classes, and you just need to set 10 outputs. Okay, so we'll use a regular neural network to demonstrate, but the same happens. So the same principle applies if you, regardless of whether it's in ConvNet or a fully connected network, because eventually you want to flatten everything in the ConvNet output and connect to a fully connected network, right? So eventually we just need to focus on the last layer. We want the last output layer to have 4 units. Okay, and each unit, the output from each unit, it actually represents it stands for a probability. The first unit, look at, we have 4 units, right? So the first unit represents the probability of that data point to be an airplane. The second is the probability of that data point belongs to bird. And the third one is for cat and for dog. So anyway, each unit represents a probability of that data point belongs to that certain label, to that certain class. Okay, so that's the meaning of the outputs. Okay, so the linear parts, it's basically the same as the regular neural network, right? So we take the activations from the previous layer, which is L-1 and times some parameter L, some bias, and we got the Z's, okay? That's the same as a first part of the neural network. That's Z, okay? So it's a 4x1 Z vector. So in the activation parts, now it's a bit different. So first we need to compute Z to the power of e to the power of ZL, okay? Because ZL is a vector, so this T is also a vector, okay? So it's basically the operation. This is what we do. We take each Z out and raise the natural base number e to the power of that Z. So we get some intermediate variable, which is t, okay? And then we need to use the t, use the normalized version of t as the activation, okay? So each unit have one t, right? And then we use the summation of all t's as the activation for each unit, okay? So this will be the final activation from the Softmax layer, okay? And so if you look at each elements, it's just the i's ti normalized by the summation. So the purpose of this normalization is to make sure that the output is a probability, is a valid probability. Okay, so it makes sure that each element, so each ti, so each ai is a number between 0 and 1, right? So that it's a valid probability. Okay, so next, for example, if we have ZL is 4, 1, -1, and 2, then we will raise, we use DL to compute the power, right? Which is e to the power of 4, 1, -1, and 2, which is a very different numbers here, okay? So then we need to compute the normalized outputs by computing the summation first, and then divided by the summation, which is the outputs. Okay, so the outputs, the activations, they are now probabilities. So these probabilities can be interpreted. Like, we mean the output means that the data point has 84% to be an airplane, and 4% to be a bird, 1% to be a cat, and 11% to be a dog. Okay, so if we want to make a prediction, we basically pick up the highest probability. Okay, so we say that it's most likely to be an airplane. So that is basically the softmax layer, what the softmax layer does. Okay. So the loss function, now it's kind of a more technical part here. So the loss function for the softmax is kind of related to the logistic regression loss, or the so-called binary cross entropy loss. So in this case, the outputs, if the outputs y hat, the prediction is like this, and the ground truth label is like that. Okay, so the ground truth label is a one hot encoding, which means that the one here means that this is the airplane. Okay, so if it's a bird, then the second element will be 1 and all the elements will be 0. Okay, so this is the encoding for the one hot encoding for the label. Okay, and for the class, for the airplane class. So we're happy about this because the prediction is pretty near to the ground truth, right? So in other case, if the ground truth is a bird, then this is a mismatch because our predictions say that it is more likely to be an airplane. Then this is something we want to penalize, right? If there's a mismatch between the prediction and the ground truth. Okay, so we use the cross entropy loss. Okay, so this loss is the weighted summation of all the y's weighted by the logarithm of the y hats. Okay, so it's basically measures the distance between the output distribution, the prediction, and the actual distribution. It measures, and also there's a negation here. So the more mismatch we found, then the higher values this loss would be. Okay, and if it's a perfect match, then this loss function would be almost 0. Okay, so for example, in the case 1, if we computed the loss values according to using this formula, we will find the loss in case 1 is pretty small, right? And in the second case, if it's a mismatch, the loss will be relatively bigger values. Okay. All right. So now if we look at the backprop, and first let's go to the let's go through the backprop propagation process for the softmax layer. Okay, so we have 4 Z's and 4 A's. Z's are the linear combinations. So we basically want to see, we want to compute the gradients for A and the gradients for Z, given the loss function in this format, right? So the loss is like this, right? The A is just the y hats, okay? And the gradients, if we take the derivative of this loss with respect to AI, to one particular component AI, then because this is the logarithm function, it's easy to find that the gradient is negative yi divided by AI. So this is the property of the logarithm function, okay? So we can think of the gradients of Zi as the summation of this bunch of chain rules, because the Z, each Z is connected to each A, right? When we compute the gradient, when we compute the forward pass, when we compute the activations of AI, all Z's are involved. And when we compute the activation of A2, all Z's are also involved, okay? So when we compute, so if our goal is to compute the gradients with of Z1, then we need to consider the gradients from all A's. Okay, so that's why there's a sigma, there's a summation function with respect to K, and the K is from 1 to 4. Okay, and we use a bunch of chain rules. We use the gradients of AK and the derivative of AK with respect to Z. Okay, so that is the chain rule applied here, and we already know that the gradients for A is like this, so we substitute into this term, and now all we need to compute is the derivative of AK with respect to I. Okay, so now this it's a bit tricky because we have the normalization terms. So we can simplify this case by differentiate whether the K is our target label or not. Okay, if it is, then the derivative will be this form. If it is not, the derivative will be this form. And if we substitute this back into the equation, we would have the gradients for Z's like this. Okay, and this can be further simplified into this form. Okay, so if you have an interest, you can go through the mathematical details, and I think it's really inspiring, and it makes you, and it draws very similar connections to the logistic regression, right? If you look at the neuron, go back to the shallow neural network chapter. When we do the backward computation, you will find that the gradients for the Z's is also the same form. It's the difference between the activation and the ground truth label. Okay, so after the gradients Zi is computed, then we can easily backprop those gradients back to the previous layer, because everything before this softmax layer is just fully connected layers, okay, which can be easily handled by backprop algorithm. All right, so that's the gradients for the softmax layer, and it's basically the same as the binary classification using logistic regression. So hopefully this gives you a helpful review of the softmax, which we mentioned a bit previously. So in the next week, we're gonna go through the rest of the ConvNets, and I will release the homework for ConvNets in later today. And there will be basically two practice. One practice is for implementing the forward pass in NumPy, and the second practice is to directly call the functions in PyTorch to define a basically a LaNet-like network, and to do image classification task. Okay, and that's it for today. If you have questions, you can let me know now or send me emails later.
Thank you.
Thank you for coming. I will see you next week.